Hello. This week's sample JavaScript program is my own version of the ELIZA program produced by Joseph Weizenbaum. Never having used Weizenbaum's original, I can be fairly sure that it differs from ELIZA substantially in both structure and grammar, but I have chosen to write it the way I have in order to keep the whole thing as simple and flexible as possible. Unlike many other versions of ELIZA that I've seen, which contain keywords and trigger phrases buried deep in the code itself, my version contains no knowledge of the ways to respond to people's input. It doesn't even rewrite words such as I, me, or mine to you or yours, or vice versa. In this way, it allows conversations to be carried out in any language. The program relies on two external files, created by the programmer, by you in other words. The first contains set phrases that trigger responses from the computer. This file is essential, because without it, ELIZA has nothing to operate on. The second is a file of group names, which associate numbers of words such as brother, uncle and cousin under a single umbrella name, family in this case. It allows trigger phrases about one member of the group to be generalized to all of them. Unlike the phrases, you don't need to create a group file if you don't want to, but if you don't, then you can't include any groups in your trigger phrases. ELIZA itself takes one or both of these files and uses them to interpret the input sentences from the user, producing what is, with luck, an intelligent reply. And these phrases do indeed need interpreting. Let's take a look at some phrases from my sample file that I offer on my website along with the program. Each phrase takes up several lines in the file, which can also contain blank lines and comment lines, starting with 2 forward slashes right at the beginning of the line. ELIZA ignores blank lines and comments. First comes the trigger phrase itself, followed on the next line by how many possible replies there will be to it. The responses themselves are on the following lines. If this rule is the one chosen to answer the user's input, one of these responses will be chosen at random. Lastly, there is a priority level for the rule, typically ranging from 0 to 10, so that some rules can be marked as more important than others. The grammar of the triggers allows for wildcards and ambiguity in the trigger phrases. An asterisk symbol, for example, matches any words to the end of the sentence, so the trigger phrase can you asterisk matches any phrase that starts with the words can you. Similarly, a hash symbol matches any single word. A single word starting with an ampersand matches any sentence that contains that particular word anywhere within it. A series of words amalgamated into one with vertical lines between them indicate alternatives, so the second rule shown will match any sentence that starts with one of the words who, what, where, and so on. Any word that starts with an @ symbol matches a group name in the group's file. For instance, in my sample group files provided on my website, I set up a group called pet, containing words such as dog, cat, hamster, and so on. So the rule I own a @pet, as shown, will match I own a dog, I own a cat, I own a goldfish, and so on. The wildcards can also be used in the responses. For instance, consider that rule in the upper right corner. The trigger phrase is my @family is a star, and it only has one possible response. The word family having an @ symbol matches any word in the family group, like aunt or cousin, and the phrase will match any sequence of words after the word a. The response, what sort of star is your @ will insert the particular family member chosen in place of the @ symbol, and the rest of the user's input sentence in place of the asterisk. Any file of phrases should have one trigger phrase that consists of nothing but a single asterisk, with a low priority value, say 0. This matches any input phrase and is used as a catch-all option, the input phrases that don't trigger any other rules. The responses offered, 4 of them in this case, are non-committal and simply prompt the user to say something. The second example phrase shows the word friend with an ampersand appended at the front. This matches any sentence that contains that word anywhere within it, as a distinct word, not as part of another word such as friendship. I've also included an example rule with a hash symbol in it. The hash symbol matches any single word, so the trigger phrase what is a hash matches any 4-word sentence like what is a kettle or what is a kitten. It won't match a sentence like what is a meaningful life. Finally, it is vital that there is no blank line at the end of the phrases file. This is due to the rather primitive way the program reads in the data from that file, and including a blank line at the end causes it to get confused. If you choose to set up a groups file, the entries in it have a similar format. First the group name, this time without the @ sign, followed by the number of entries in the group, and then the entries themselves. In these examples, the three words love, adore and cherish are associated under the group name pos emotion, so any trigger phrase that contained a word @pos emotion would match any of those three words. Again, the file should not end with a blank line, as it confuses the program. That's something you might like to change to make the program a little more robust. Here's the screen view of the program. You can see the two text areas of the different lists, plus two input fields, one for the user to type his input and one for the program to respond. The input is handed to the computer when the user presses the Enter key. As the conversation proceeds, the interactions are added to an HTML division at the bottom of the screen, so that the whole thing can be tracked later and copied to the clipboard if you want. As usual, we start with the global variables. The trigger phrases will be stored in the array triggers, with the responses that they produce stored in responses. Of course, each phrase can have several responses, so the elements of responses will themselves be arrays. Each trigger phrase has a priority level stored in array priorities and also a shackle value. A shackle for any trigger phrase is normally set to 0, but when the phrase plus response is chosen by ELIZA, it is set to 10. When comparing priorities for the matching rules, ELIZA subtracts the shackle values from them before the comparison. Any shackle value above 0 is reduced by 1 with every phrase ELIZA produces. This discourages the program from picking the same phrase too often after it's last been chosen by demoting it temporarily. The variable num_phrases stores the number of phrases. Yeah, I know this could be achieved by looking at the length property for the array, but I've done it this way for convenience and ease of reading. The groups are stored in array groups similarly, with the members of those groups being stored in array related. Similarly, each element of related is itself an array for all the different members of that group, and the number of groups is given by num_groups. When the user types in the input and presses Enter, that input is split up into words and stored in a variable WDS, which will of course be an array. The number of words will be stored in num_WDS. The variables specific, rest, and GP_word hold part of the input sentence for use in the response. If a wildcard, such as a hash symbol, an asterisk, or a group word is used in a trigger, then the matching word or phrase in the input is copied into specific, rest, and GP_word respectively. Just before the response is displayed, the relevant symbol is replaced by the contents of the appropriate variable. The variables line and lines are needed when reading data from the text area, and are global as they are thrown around between different functions. Here you see the HTML code for the text field in which the user enters his phrase called input text. It responds to every key press to detect whether the enter key has been pressed, and if so, it calls the function processInput. The function checkEnter is a standard way of checking for any particular key press on a web page, with the appropriate number substituted. The number 13 here is the character code for the enter key. The function loadPhrases reads the contents of the phrase's text area into the variable s and splits it into separate lines in variable lines, using the end of line character as the separator. The variable line is set to 0 and it steps through the lines extracted, reading the data. The function getLine is used to get the next line in the text area that isn't either a blank or starting with the 2 slashes to indicate a comment. It does this by looping round and round, increasing the variable line as it goes, until it finds a suitable line. As long as there are lines left to read, loadPhrases reads the trigger phrase first, ensuring it is in uppercase, followed by the number of responses. It then declares the appropriate element of the array responses to be an array in itself, and reads the next, however many lines it is, in as the responses themselves. Finally, it reads the priority value of this trigger phrase and takes the opportunity to set the shackle value for that phrase to 0. Then num_phrases is incremented, ready to read the next phrase into the next slot. This is the reason why there mustn't be a blank line at the end of the text area holding the phrases. If there is, then the condition about line being less than lines.length is still true after the last phrase and its entourage have been read, and the loop goes round one more time, expecting to find another phrase. This causes the program to crash, so don't do it. Function Regroups works in a similar way, reading the contents of the text area load groups and putting the group names in array groups, and the members of those groups in array of arrays related. Again, don't put a blank line at the end of the text area for the same reason as before. It will confuse the program, which will fall over and catch fire. Comparing the code for this and load phrases shows that they are almost identical, with only the minimal changes between them. In fact, there are only 4 more functions in the entire program, but 3 of them are very large and work together to turn input phrases into appropriate responses. This is the start, just the start, of the function processInput, which is called when the user hits the enter. The first thing it does is to grab the phrase entered in the element input text. It converts it to uppercase to make sure that it matches the trigger phrases, and then splits it into words in the variable WDS, with a number of words in num.wds. It then has to go through all the phrases, determining which one best matches that input. This is done using a variable current score, against which the priority levels of all matching phrases are compared. Current score is initially set to an arbitrarily low value of -1000 to ensure that even the weakest match can beat it. Even the catch-all phrases with their priority level of 0 can beat -1000. The for loop goes through all the phrases, calling match phrase to determine the match score. If the score is greater than the current best value, then that becomes the new current best, and the index of that phrase in the list is stored in variable current phrase. We will be using that value later on to construct the correct response. In fact, we'll be using it right now, as this is the latter half of the function processInput. The best matching phrase has been identified, and its index stored in current phrase. The first 3 lines shown on the screen choose a random reply from the ones available in the responses array. The last of these lines hands the reply to the function alterResponse, so that it can replace any of those wildcards. The adjusted reply is placed into the text field myResponse, and both the user's input and computer's response are added to the conversation at the bottom of the screen, the user's input in blue, the reply in red. The shackle value for this phrase is set to 11 to demote it down the possibilities list. Now, I did say I would use the value of 10, but in a couple of lines' time, all the shackle values are being reduced back down towards 0 anyway. The function match phrase is even longer, and its purpose is to produce a score for any phrase in the list when matched against the user's input. This function won't determine whether this phrase will be the one that wins the competition. All it does is produce a score value. Here is the first part of it. The first thing that happens is that the phrase is split into words, stored in the array trigger WDS, with a number of words in num_trigger. The potential score for this phrase, assuming it matches, is the priorities level for this phrase, but reduced by the shackle value. Firstly, the phrase is checked to see if it's the catch-all phrase, i.e. a simple asterisk. If so, the score has been determined and it is returned. Assuming that isn't the case, the next step is to perform a word-by-word comparison to see if all the words match between phrase and input. This is done by setting match found to true, i.e. assuming they do match, and then comparing the words individually, and as soon as a pair of words are found that don't match, match found becomes false. Of course, when I say match, I don't mean that they must be identical, since we have all those wildcards, but they must be compatible. If the input does match the phrase on this word-by-word basis, then again the function terminates by returning the score value. Next, we have to determine whether the input matches any phrase that is a contains phrase, i.e. just a single word preceded by an ampersand. This is like that phrase that was simply the word friend that you saw earlier. In this case, the variable containWD holds the single word in the phrase stripped of its ampersand, and each of the words in the input is compared to see if it's compatible with it. If the word is found, then again we have a sentence match and the score is returned. Finally, we have to determine whether the input matches any standard phrase that ends with an asterisk. Essentially, the input sentence and phrase must match on a word-for-word basis up to the word before the asterisk, and after that anything goes. The variable x is used to hold the last word of the phrase. If this word is the asterisk, then the for loop goes through the phrase and input, seeing if they match as it did before, but this time only up to word x-1. That's enough to get a match in this case, and it sets the variable match found to true. The remaining words in the sentence are then strung together and stored in the variable rest for use in the response of this phrase, should it be the highest scoring one. The last line of the function returns a default value of -9999. This is the lowest possible value and simply means the input sentence didn't match the phrase in any way. One more large function to go, and that's the function match that compares two individual words, one from the input, the other from the phrase. Firstly, the function detects if the word from the phrase is a hash symbol. This matches any single word in the input, so the function returns true, but only after it's stored the word that the user really did type in the variable specific for later use. Of course, it's always possible that the two words simply are the same, a direct match, and if they are, it returns true. After that, the function checks to see if the word typed is one of a series of alternatives joined by vertical lines, which are split up into individual words in the array or WDS. It goes through the list, and if any element of or WDS matches, then again a match has been found. Finding whether a word matches a group word such as family or pause emotion is slightly harder. Firstly, we take the group word, which we know because it starts with an @ symbol, and work out which group it comes from. The for GP loop goes through all of the groups, working out which of the groups the word matches. If the word were family, for instance, this loop would identify it with the family group. The index in the groups array is stored in which GP. Of course, it's always possible that the group referred to doesn't exist. You might have included a phrase, but forgotten to include the group that goes with it. That's why the next part can only be done if which GP has been set to a sensible value, rather than the starting value of -1. Assuming the group has been found, another loop then goes through the members of that group, trying to match each of the members with the actual word typed. If it does in fact match, then the variable GP word is set to the word in the input sentence, and the function returns the score for the phrase. And after all that, if the input word hasn't matched anything else, then the two words simply don't match. The function returns false. The only other function to mention is alter response, which is the final step before ELIZA's response is displayed on the screen. The replace function is used to replace the hash symbol, if present, with specific, the asterisk, if present, with rest, and the @ symbol, if present, with the group word identified. Phew, that was quite a program. 207 lines of JavaScript, and even so, it only provides the most basic functionality. You'll notice that the result is very unpolished, with responses being a mixture of upper and lowercase letters, missing punctuation, or inserted in the wrong place. Also, even with a good set of phrases and groups, and the sample I provided on the website are hardly that, the program suffers from all the drawbacks that Weizenbaum's original did. If you want to improve it, and I'm sure you do, then that should really be the correct approach. Give the program a bit of memory, so that it can at least remember what topic the user's talking about. Perhaps it could store information about the user, at least throughout the conversation. Without information, there's no way that this version of ELIZA can hold anything resembling an intelligent conversation. Fortunately, the ways in which computer programs can store and process knowledge is the topic of the next lecture, so it would be a good idea for you to subscribe to the channel so that you don't miss it. I would also like to hear in the comments below how you fared with this version of ELIZA. As usual, the code on my website can be found by following the link in the description. Did you use my sample set of phrases and groups? Did you add to them, or did you use your own? What were the results like? And how long was it before the computer started to say some really stupid things?